Okay, so initially I was thinking we won't have time to do this, but because we have one more class on Friday, I just thought I'll give you a crash course on power amplifiers. Okay, so obviously, you know, these are all probably single or two transistor circuits as a power amplifier, and usually people take a year or two to design them. Okay, so don't take it too lightly. Sometimes more. Okay, and it's very sensitive to a number of parameters. Okay, so what we are going to present today is a very basic theory. Okay, and we're going to cover. We'll try to cover at least maybe like 5 or 6 types of power amplifiers. Okay, so I will just go through them quickly. Okay, so I mean normally I'd want to spend maybe 2 or 3 classes at least on this, but since we don't have time, I just decided give a quick introduction. So of course you can have narrow band or wide band. So first classification is that is the basic classification, but the more important one is linear or switching power amplifiers. Okay. So linear PAs will be used in cases where you have amplitude modulation. Okay. Whereas switching PAs will be used in let's say PM or FM type of situations. Okay. So the switching PAs are typically constant envelope. Okay, so the output envelope, the output amplitude does not change significantly with input amplitude. Whereas in linear PAs, you get some specific gain, almost like an amplitude, like a voltage gain. Okay. So what kind of trade-off do you have in the design? So rather, what are the parameters you are interested in? Okay. So of course, it's a power amplifier, so you're interested in power gain. You're interested in linearity, the output power, and the efficiency of the power amplifier. Okay. So you will see this actually has 2 classifications. We'll look at both. There are 2 types of efficiencies. So if you look at the classical PAs, so they are the linear types of PAs. So class A, you would have studied a lot of these things in your analog electronics course, I'm sure. Right? Class A amplifiers, class AB and class B. I'm sure you have studied those, right? Okay, so you classify them based on the conduction angle. So for the amount of time of the during the cycle when the transistor is actually on, it's conducting. Okay. So the class A has a 360-degree conduction angle. Okay. So first of all of these classical PAs will have a standard type of topology. Okay. Okay, This is a standard topology for all of these, class A, AB, B, C. Okay, yes. Okay, so the conduction angle, so so let's say it's running at a particular frequency. Okay, so it will have a certain time period. Out of the time period, the transistor itself can be on for the full time period or can be on only for part of the time period. Okay, so you can classify it based on the amount of time the transistor stays on. Okay, even though the transistor does not stay on, what you will see is the resonant circuit makes sure that the output voltage is still sinusoidal, even though the output the current through the transistor is not, or the voltage across the transistor may not be. Okay, so finally, I mean, so that is one big difference here in RF power amplifiers, because you can actually use resonant circuits to tune out the unwanted harmonics. Okay, and at the end of the day, the conduction angle actually depends on the biasing of the transistor itself. Okay, so this is a kind of a standard topology which you are going to use for all of these classical PAs. Okay, so you have a very large inductor, you have a very large capacitor. So the large inductor makes sure that it has, so it will make sure that there is a constant current flowing through it. Okay, it will act like a current source. And the other advantage is it actually biases your output at VDD. The capacitor, the BFC, the big fat capacitor, makes sure that there is no DC current flowing through your load. Okay, this LC resonance circuit makes sure that you don't have, if there are any, remember that at resonance it's a high impedance, so the current IF omega naught flows through the load, all other currents are bypassed. That is what you want to achieve. Okay, so at the end of the day you want to get a sinusoidal current at the output. Okay, so this RL can of course be, for example, 50 ohm of the antenna, or you can do some impedance matching and change it. It's up to you, depending on what power you want to deliver. Okay, so now if you can actually plot, so the drain voltages and the drain, the VDS of the transistor, drain source voltage of the transistor, and the drain current. Okay, and you'll see what it looks like for different types of PAs. It will be slightly different. So let's plot VDS and ID as a function of time. Okay, so it's biased around VDD. Okay, and for many of these cases you can assume that VD sat is very small compared to VDD. That's what we'll do. Okay, it makes our calculations easier. And you have some DC current and okay, you will have some current, and obviously you make sure that for class A you make sure that ID is always greater than 0, so the transistor is always on. Okay, so the maximum voltage at the top is 2 VDD minus VD sat, and at the bottom it's VD sat. Quite often you will see people approximating it to VDD. Okay, so that the overall amplitude is approximately VDD. Okay, sorry. So what happens when you have very large current? Yeah, you are right. So the current and voltage will definitely be out of phase. Okay, they will be out of phase. You are right. Okay, And of course the ideal case you want is so you want the current to just cut off, okay, at the minimum, and you can find the conditions for that, okay. So you can bias it such that the current just cuts off and you get maximum amplitude, so approximately VDD. You can say ID okay, or minus IR sin omega naught t. The sign doesn't matter that much, okay. Okay, so the output is nothing but the DC minus the drain current. Okay, so let's maybe stick to our convention. Okay. So now V out is RL, which is sin omega naught t, and your VDS is okay. Okay, you can find expressions for VDS. You'll see why we are trying to find this out. Okay, what is your P out? I mean, you can do either I out times V out or V out squared over 2 RL, V out squared over RL, whatever you want, where they're all RMS quantities. Of course, the power is going to have a second harmonic component and a DC component, right? So you can plot your power. So it's going to be it's going to have something like this, a sine square kind of behavior. Okay, so now to calculate efficiency, we are going to calculate the DC power, okay, from the power supply. What is this? It's VDD times IDC. Okay. If you assume that M1 just cuts off, so you want to get the best efficiency, right? So the best efficiency is when M1 just cuts off, and at that point your IDC is the same as IRF, the amplitude. Okay, which means you can write it as VDD times IRF. So your drain, this is called drain efficiency. Okay, it's nothing but P out over PDC. Okay, and what is the maximum swing we have at the output? It's nothing but IRF times RL, which is nothing but VDD. So you want maximum VDD swing. So efficiency is 50%. This is the maximum efficiency because you have biased it optimally such that you use the whole dynamic range of the current and the voltage. Okay. Now you're also going to define something called the normalized power output capability. Okay, so we'll call it as PN. So this is defined as the ratio of the maximum power you are delivering to the load over the product of the peak values of VDS and ID. So this basically gives you an idea if you're delivering a certain amount of power, how much stress are you placing on the device? Okay, because the more the voltage swing at the drain of the transistor, the more voltage stress you have. If you are delivering a lot of current, running a lot of current through the transistor, it will cause a lot of current stress. Okay. So in this case, PO max is nothing but, so output swing is VDD. So your PO max is VDD square over 2RL. What is VDS max? Is nothing but 2 VDD. Okay. Times what is ID max? Is nothing but 2 VDD over RL. This happens to be 1/8. Okay. So this is somewhat high. Okay. So you want, if this number is very large, then it means you are actually placing less for a given amount of power. You are actually placing less stress, right? If the number is very small, that means that the VDS max and ID max are very high compared to related to the power you are trying to deliver. Okay, this is 1/8. Now similarly, you have a class B amplifier. Conduction angle is 180 degrees. Okay. In other words, so let's say we again plot VDS and ID as a function of time. The output is still biased at VDD. Okay. Okay, but the difference is it is going to conduct for only half the cycle. It's going to look, the current through the transistor is going to look something like this. Okay. Again, so based on this waveform, you can find out the fundamental value of the current and find out what goes through the load. So that is what will go through the load. Okay. Okay. So in this case, it will be the way I have drawn it. It will be T/2 to T. Okay. Times. Okay, this is the fundamental portion of the current. This happens to be IRF over 2. This is IRF. Okay. So again, you can calculate your efficiency and your PN, normalized output power capability. I'm rushing through this because I assume class A, class AB you guys have already seen before. So we need to get to the real. So these are of, I would say, of somewhat limited value in many modern systems. They do have some value, but the other types of the switching power amplifiers are more often used because they can have higher efficiencies. Okay, so you can show that the maximum efficiency is pi by 4. Okay, you can again calculate PDC and PO. Okay, you can show that this happens to be pi by 4, approximately 78%. And similarly, you can show that PN is actually the same as the class A case. Okay, it's there in the notes, so you guys can take a look at it. I want to kind of rush through and get to the other section. So what does this mean for the way you bias the transistor at the input? So obviously it's all to do with biasing, right? You want to have a certain amount of current, so which means okay, so let me do one thing. Okay, so you're going to add some V bias here. So this is the biasing capacitance, and you have some biasing resistance. Okay, so let's say Vs is your input is some sinusoid. Okay, so for class A, you want Vb to be greater than Vt plus Vrf. Okay, so that at the lowest end of Vrf, okay, the transistor will still be on, whereas for class B, the bias voltage will be at Vt. Okay, which means when it's above Vt, the transistor will conduct. When it's below Vt, the transistor will not conduct. Okay, now you can also bias it such that the Vb is actually less than Vt. Okay, which means the transistor will conduct for less than 180 degrees of the cycle. Okay, in other words, whenever your input goes above Vt, the transistor will conduct. For most of the cycle, it will actually be off. Okay, this is your VDS again. Now if you look at your current, you are going to have just the top portion of a sinusoid. And this 2 phi is called the conduction angle. Remember, 2 phi is the conduction angle, not phi. Okay, this is your ID. Okay, so now for an arbitrary conduction angle, you can find expressions for your DC current, for your power and so on. Okay, so it happens to be some function of phi. So you can show that phi is okay. your so-called bias current happens to be the offset current. So earlier we assumed that it was an IDC plus IRF sin omega naught t. So that offset current is actually negative, obviously, because now you have a conduction angle less than 180 degrees. And you can find expressions for your actual average current through your transistor, which will be ID. You can show that this is nothing but IRF over pi times sin phi minus phi cos phi, where phi is the half conduction angle. Okay, and similarly you can calculate expressions for the fundamental. You can show that the fundamental is IRF over 2 pi times 2 phi minus sin 2 phi. Okay. So you can go through this, you can look at the notes. The thing to remember is you can find expressions for the efficiency in terms of phi. Okay, you can find expressions for the output power in terms of phi and so on. So I'll just give you this. So your maximum efficiency, you can assume that there's a swing of VDD at the drain to get your maximum efficiency. And that happens to be, I'll show you what happens. So it looks like 2 phi minus sin 2 phi over 4 times it looks like this. Okay, so if you try to get maximum efficiency from this, you keep tending. It so happens that happens at you'll get a value of 100% when phi is actually 0. So obviously you don't have any output power. Okay, so that's an obvious problem. So the trade-offs are not very different in this amplifier. Okay, so it is just a natural extension of your class A and class B. So let's look at your switching PAs. So we look at 3 types. So okay, so we look at a class D, a class E and a class F. Okay. So for the class D case, we look at a push-pull kind of case. So far we have just been seeing a single-ended power amplifier. So this one we'll look at a push-pull. Okay. Okay. So this is going to make sure that so let's call these M1 and M2. Okay. So what's going to happen is when you have a certain drive at the input, for half the cycle M1 is going to conduct, for half the cycle M2 is going to conduct. The difference is between the earlier cases and this case is that the main idea of switching PAs, you are going to use your MOSFETs as purely as switches. Okay. The main reason you want to do it that way is because for an ideal switch, you know that when your switch is on, what is the voltage across that? Ideally it's 0. Okay. So you have current but you have no voltage. So the power dissipation is 0. When the switch is open, you have voltage but no current. Okay. So you want to tend towards such a case. Okay. And you are going to try to use the MOSFETs in such a configuration. Okay. So now you can actually plot the voltages. Okay. So let's take M1, we can plot the voltages at the drain of M1 and the current, and then we will also plot the secondary. Okay. Okay, the voltage at the drain will look something like this. Again, the output is biased at VDD. When the switch is on, it goes to 0. When the switch is off, it goes to 2 VDD. Okay, and it's more like a square wave. And if you plot ID1, you have current here, you have current here. So whenever the voltage is 0, you have current. Whenever the current is 0, you have, whenever the current is 0, you have voltage. Okay, that is the ideal case you want. And you get a full half sinusoid. Okay, and if you look at the current through the other transistor, it will provide the other half cycle. That's why it's a push-pull amplifier. So let us say the voltage in the secondary is Vs2, secondary of the second transformer is Vs2, and the current is Is2. Okay, so we are going to plot those two. So you are going to get a nice square wave with both sides. Okay. Similarly, if you look at Is2, sorry, you are going to get a nice sinusoid on the other side. The main reason is so note that one difference is you have a series resonant circuit. Okay, why did we have a parallel resonant circuit? So if you look at the linear power amplifiers, when the transistor is on, because the inductor is cutting off any current, it is behaving like a current source, like a signal current source. Okay, so you want to bypass the extra harmonics through a shunt resonant circuit. In this case, you know that the switch when it's on is actually low impedance. Okay, so that's why you are going to use a series resonant circuit. Okay. And similarly, you can find out your drain efficiency and so on. And let's just find out what that is. Okay. You can show that your power handling capability is, actually we won't look at the class D, we will do that for the class E and class F. But for this one, you can show that it is 1 over pi. Okay. Actually, I should say lower stress. Okay, because the number is slightly higher than the other case. Okay, so now the only thing you need to have is, you're assuming that the switches are pretty fast. Okay, they are turning on and turning off very fast. Okay, that is an assumption you are implicitly making when you are drawing all these waveforms. So in a real case, this may not be very applicable to high frequency PAs. So class D is used quite often in, for example, audio amplifiers, but in RF power amplifiers, they may or may not be that useful. What is more useful are the class E and class F architectures. So the idea is very similar. Okay, you want to use it as a switch, so that's the key idea as always. But the difference is, The difference is you are going to try to bias it such that before the current starts to flow, the voltage goes to 0. Okay, that's what you want. You want to bias it in such a way. Okay, so that you make sure there is no overlap between the current and voltage waveforms. And to do that, you are actually going to use a higher order, slightly higher order reactive network. Okay. This is your RL. Again, you can plot your VDS and ID for these cases. Okay, so you can show that. Let's see. So let us say your VDS waveform goes like this. Okay, it turns off, and your ID actually turns on after this. Okay, so remember that you are going to have the second cycle. And ideally you want something like this. Okay, the problem is you have taken, you take very good care of the on cycle, but in such an architecture what you'll see is, you always see the off cycle. Okay, when the transistor turns off, you will see some power leakage, okay, into the transistor. So there is actually a classic reference. Okay, it's from 1975. Okay, by SoCal and SoCal. Okay, that's the name of the authors. It's actually in JSSC 1975. I'll put up the paper on the website. I think it says a new class E, a new class of high frequency single ended power amplifiers. I think that's the title. Okay, so it's in Journal of Solid State Circuits in 1975. Okay, and he actually gives you all the design equations you need. Okay, for this, and I'll just kind of list out, because the main design equations are, how do you choose C1, L and C2, right? Those are the important ones. So of course you have a certain Q, your inductance is Q times RL over omega. Okay, this is the expression for C1. Okay, so it's kind of, they've derived a certain set of design equations. Okay, and you can show that your P out max is 2 by 1 plus pi square over 4 times VDD square over RL. Okay, don't worry too much about these numbers. Okay, so they are just specific design equations, but you can always refer to them. So again, you can decide your output power handling capability. Okay, that happens to be 098. Okay, approximately 0.1. Okay, the other case we had even for the class A and class B we had what 1/8, which is 0.125. So this is actually also a high stress, okay, amplifier. And actually one more thing to remember is I forgot to, yes. So because you are trying to sharply turn on and turn off these devices, your peak voltage and peak current are actually quite high because you have an inductor, right, and a reactive network. So it turns out this is almost 3.6 times VDD. Okay, and this is almost the peak of the current is almost 1.7 VDD over RL. So that itself should tell us that it's actually a very high stress, okay, situation for the amplifier. Okay, so next we'll look at the class F amplifier. The idea here is actually slightly different. Okay, so what you're going to try to do is so let's say this, you're going to use a transmission line of a certain length. Okay, so you're going to use a lambda by 4. So you know the properties of the lambda by 4, right? So what happens? So if you have a, so let's say what is En? Z0 squared by ZL, right? Okay, so you're going to use this. So what happens if you put a lambda by 4? So okay, so typically if you have these kind of reactive network when the transistor is switching, you're going to get the fundamental plus harmonics of the fundamental. Okay, so what you actually want to filter out are the harmonics. Okay, so it turns out that if you do this, okay, so first of all, this is tuned to omega naught. Okay, so at omega naught it's an open. For all other frequencies it's a short. Okay, what is this transformer going to do? At even multiples of omega naught, so let's say 2 omega naught, 4 omega naught and so on, this transmission line is going to have effective length of n times lambda over 2, right? At short circuits, at odd multiples of omega naught, you are going to get 2n plus 1 times lambda by 4, okay, and that is also going to give you, so this, okay, at 2n plus 1 omega naught, this parallel resonance is going to be a short, so it's going to create an open here. Okay, so you're going to make sure that only omega naught flows through the transformer. Okay, yeah. Okay, and if you plot your again you can plot your VDS and your ID. Okay, so it's going to go from 2 VDD to 0. And current is going to look like this. You can show that the peak value of the current is 8 VDD over pi RL. Okay, that's actually very easy to do. So all you have to do is, you know this, find out fundamental is just 4 by pi times the amplitude. Amplitude is VDD, right? It's actually fairly straightforward. So now you can find your efficiency. So this is your fundamental of this guy. This thing is nothing but okay. Eight VDD squared over pi square RL. Of course, your ideal efficiency is 100%. Ideally, okay, you're assuming that the harmonics are ideally completely rejected. Okay. So in practice, you can actually get a better efficiency than the class E. Okay, because you're actually using resonant circuits to filter out the higher harmonics. You can show that your Pn, okay, is this is your VDS max, this is your ID max, so the normalized power output capability is approximately 0.16, okay, little bit better than the linear PAs and definitely better than the class E. And you can come up with a, so of course you don't want to use transmission lines in many of these because they'll get too long. Okay, so the next thing to do is use lumped LCs, because you know you can start using, what you are trying to do is very simple, you are trying to reject out certain harmonics. Start using, you know, tuned circuits, either series or parallel tuned circuits to reject harmonics. So for example, this is tuned to omega naught, the original one. You can tune these to 3 omega naught and 5 omega naught. So that those will be the major components. Okay. So the one thing you have to remember is, in all cases your output voltages are all functions of the VDD, so they are actually constant envelope PAs. Okay, so they are very good with phase modulation. So you can get so in cases where, let's say, you have GMSK or, you know, PSK, something like that, they'll perform very well. Okay. Now there are obviously extensions to this. So if you want to perform amplitude modulation also, people tend to use these because they are still very high efficiency. but then this is your VDD. You can now modulate your VDD. So if you change your VDD, your output envelope will change with your VDD. Okay, so you can have supply modulators. Okay, you can take from a DC power supply and take your amplitude signal and vary your VDD based on the amplitude, and that will directly get transferred onto your output signal. Okay. So quickly, other design considerations. So we talked about what is called drain efficiency. Okay, but you have a second definition called, it's called power added efficiency, and you'll see from the way it's defined as P out minus Pn over PDC. The reason you want to define it this way is because if you have a PA, okay, which gives out no power gain, okay, it looks as if it has a very high efficiency, but in reality it doesn't, because you're not adding any power. Okay, so this is a good way. So in which case, if there is no power gain, your power added efficiency is actually 0 for the PA. So obviously this is less than the drain efficiency, okay, which is just P out over PDC. So the other thing is stability. So you have parasitic gate to drain capacitors, which will end up degrading your stability of the PA, and especially now you have very large power gains, your PA is going to be very sensitive, okay, to your CGD. Another very important problem, breakdown. Okay. Switching PAs may or may not have, okay, but definitely the linear PAs have it. Okay, switching PAs may not have as big a because you are just depending on a switch, right? You are not transferring any input output signal, so switching PAs may not have such a big problem. Breakdown voltages. Okay, so we considered, we are looking at cases where your output is swinging, much higher. If you look at the class C, it's swinging as high as 3.6 times the VDD. So definitely your circuit is going to be very sensitive to breakdown. Okay, so you periodically, if you start stressing it to such a high voltage, so what could happen is, if you don't design it properly, so you have to look at different kinds of breakdowns. Okay, so the first breakdown is drain bulk and source bulk diodes. Okay, so if you are having such a large swing at the drain, okay, so typically it will be a function of VDD. So if your VDD is typically like, let's say 1.2 volts, your diodes will not have a much larger breakdown than maybe 3 volts or something. Okay, maybe 2 to 3x of your VDD, not much more. Okay. The other thing is, you have to worry about what is called TDDB. Okay, time dependent breakdown. Okay. Okay, the reason it's called, time dependent dielectric breakdown. Okay. So the main reason is, it's called time dependent is because, so now you are working with very large powers, you will have these very high energy electrons which can go and create traps inside the oxide, and it's actually a cumulative effect. Okay, because what happens is, these traps, they'll eventually slowly reduce your threshold voltage of your device. Okay, so it's a cumulative effect. So slowly you'll reach a point where your efficiency will keep dropping till such a point where it will be useless. Gate rupture. So obviously now your gate, okay, so gates are getting thinner and thinner, right? So you have to start worrying about fields in the gate, which can actually break down your gate oxide. Okay, and the last one is called punch through. So what happens when you have very large VDSS? The depletion region of the drain keeps extending until it actually hits the source. Okay. So if that happens, you completely lose your channel. Okay. Ideally, your channel extends from the source to a certain region. After that, you have the depletion region. If your voltage fields are high enough, it will get pushed out until it hits the source. Okay. Okay. So those are the breakdown phenomena. And the last thing you have to worry about is, well, not the last thing we are going to consider in class is the so we talked about, in class, the kinds of impedance matching we talked about were all small signal impedance matching. Okay, small signal S parameters. Okay, so in reality, when you have signals of such large amplitudes, quite often your passive devices will still be linear, but your active devices, the input impedance is no longer linear. Okay, so in which case you have to worry about large signal impedance matching. Okay, not small signal impedance matching. So in other words, if you look at the simulator, instead of doing a simple S parameter analysis, you will be doing what is called a periodic S parameter analysis. Okay, so you will again be doing the dot steady state analysis followed by your S parameter. You need to find out your so for example, your input gate source capacitance will no longer be 2/3 WLC aux. Okay, there will be a lot of other effects going on in there. Okay, so we'll stop here for the PAs. Okay, and that was a